Hello everyone. This video will talk about 6.3 and 6.4. 6.3 is our third way of finding volumes by slicing. We already talked about the disk method, the washer method. In certain cases, those two methods alone can be cumbersome as far as finding the volume of some rotated region. So with the cylindrical shells approach, it'll allow you to be more selective about what axes you want to integrate through. So what I have here in example one is actually a problem that we might not totally finish, but I'm just going to set it up and show you kind of why another method might be a lot better. So let's imagine this were our actual problem. It says find the volume of the solid obtained by rotating this region. The region bounded by y equals sine x plus 1. We have y equals 0, x equals 0, and x equals a half a pi. And we're rotating this around the y-axis. So it says make a sketch of the situation. So let's do that part. So first off, for y equals sine x plus 1, so sine of 0 is usually 0, but then we add 1, so that'll bring me up here for this piece of the function. Sine of pi over 2 is 1, so 1 plus 1 brings us to 2. So we'll have this kind of piece of the sine curve happening in this region. And then I would also have y equals 0. I have kind of this part of the axis also. X equals 0. And then x equals pi over 2. So within these four boundaries, we have this region that's defined. Okay, if we are using if we're rotating around the y-axis, that means if we're using disks or washers, that we would need to orient our kind of sliver of this area pointing at that y-axis. Right, so we'd have this sliver. But the thing is, over here, we have a change occurs, right? So where right here, we can use the disk method because this area is literally attached to the axis of rotation. We can just use the disk all the way from here to 1. But then from 1 to 2, we would need to use the washer method. So this would be a region, maybe I'll just make it a little more different, but this region here would require washer. And then this region here, if you can tell kind of what I'm shading there, would be disk. So you'd be able to use actually two different methods within one to figure out this volume. So let me write it out. So we would have, maybe I'll call this, this will be my section 1, this will be my section 2. So the volume of 1 would be given by, well, we'd integrate along the y-axis, right? Because this is pointing at the y-axis. I'm going from 0 to 1. And my outer function would be, let's see, this function here. So x equals pi over 2. So that'll just be the function. So I'll have pi times pi over 2 squared, and then dy for this piece. That's the volume of this first chunk. right? Here's the pi times the radius squared. And then we're integrating just literally from 0 to 1. And then the volume of region 2 we would need the washer method here. So maybe I'll keep it in light blue. We'll go from 1 to 2, sorry. Right now I'm going from this region, 1 to 2. And the outer function is still this pi over 2. So I'll have pi over 2, maybe I'll just bring the pi out front before I forget about it. Pi over 2 squared, that's that outer function. And then minus this inner function squared. So this inner function here is y equals sine of x plus 1. So since everything is with respect to the y-axis, what I'll need to do is actually think of this as, well, if I solve for x, basically, I would subtract over 1. I have y minus 1 equals sine of x. And then find the inverse sine. So I'd have inverse sine of y minus 1 equals x. So that's actually the function that I'll need to square. So down here I'll have sine inverse of y minus 1, and then I need to square that. And those square brackets, and then dy. So the true volume would be the sum of these two. Right, so the actual volume would be this integral from 0 to 1. I'll just go ahead and take the pi out front. Then we have, I guess, pi squared over 4 dy plus this other integral, 1 to 2. And I'll just actually leave it. I'm not going to actually fully carry out this integration. My point is just to show you, hey, look, this is difficult. And there's another method that we can choose that's less difficult. Okay, so I'm just going to stop here. This would be the volume, but this is difficult. So the Shell's method may be better, just saying. Maybe better. Okay, so let's take a look at the Shell approach to this same exact problem. Okay. Here's a reminder of the formulas that I was just using. So here's the disk method. Here's the washer method. These are from our previous sections. Here is the Shell method. So if we're integrating along x from a to b, then we would take, if we're rotating around the y-axis, then we actually take a slice that is no longer pointing at the y-axis. We're taking a slice that's pointing at the x-axis. So instead of integrating with respect to y, since we're rotating around the y-axis, we can actually still integrate with respect to x, even though this sliver is getting rotated around this axis, this y-axis. So what you would have is some radius x. So there's this radius x. If it's being rotated, that's like finding the circumference. So you have 2 pi r, basically. 2 pi x is acting like 2 pi r. And then the height is f of x. So this is why this is generating a volume if you differentiate or integrate over x. So let me draw this same one here on page 141, same problem that we were doing. So we have this again, this kind of piece here. We have these axes as a boundary as well. and then also pi over 2. So we have this region here. I'm still rotating it around the y-axis. With the shell method though, what I'm able to do is take a vertical slice Okay, so this is actually pointing at the x-axis, which tells me that I'm going to need to integrate across x instead of y. Okay, so the method says, I'll write it here, the volume is from a to b, we'll go from 0 to pi over 2, and then it's 2 pi times x times f of x dx. Okay, so the volume will be, well, I'm integrating across x, so the region is just in existence from 0 to pi over 2. So I'll have 0 to pi over 2, and then it says to take 2 pi times x, and x is meant to be the radius, and since this region is attached to the radius, or sorry, to the axis that we're rotating around, I don't need to make an adjustment. I'll do one later where we need to make a bit of an adjustment. So I'll just write x, and then times f of x. And that governing function that is defining the height of this sliver is this trigonometric function here. Right, so I'll have sine, oops, I'm writing down here again, sine x plus 1. That's my function, and then dx. Okay. So, let's see, we can now write this integral from 0 to pi over 2. Maybe I'll bring the 2 pi out front. Distributing the x, I have x sine x plus x. And then this would all be with respect to dx. All right. So I think I'm going to wait to actually evaluate this, because to actually evaluate this one, we actually need something from a different section. So this would be, though, the volume. And you can maybe use your calculator now and type that in, and it'll spit out the volume. Just comparing it to what we had before, you can see that it's a much simpler thing. Right, this was our volume before. But my goal isn't to evaluate these integrals at the moment. I was just wanting to show you, hey, look how much more complicated this one is with respect to finding this volume than this one. But they're going to produce the same value. Let's see, let's try another one. So 142, I'm hoping we can actually evaluate this one. So example 2 says define R as the region bounded above by this graph, 1/8 x squared, and below by the x-axis over this interval, just 4 to 6, using the method of cylindrical shells to find the volume of the solid of revolution formed by revolving R around the line x equals 1. Make a sketch of the situation. All right. So we're just looking at this region from 4 to 6. So maybe I'll evaluate the function at 4, and then I'll evaluate the function at 6. So if you plug in 4, we have 1/8 times 4 squared, we get 2. So at 4, this function is at 2. And then at 6, if I go back, replace that 4 with a 6, we get 9/2. So 4.5. So this would be 5, right? This would be 4.5. So we would have this kind of piece of the parabola here, right? And it says below by the x-axis. So we also have this boundary. And around the line x equals 1. So we have this as our axis of rotation, actually. So this is one of the first ones where we're not rotating around one of our primary axes, right? We're rotating around x equals 1 in this case. So we have, let me just define this section. We have this area, and we're rotating around this axis here. So something I can do if I want to use the cylindrical shells is I can actually orient this still with respect to x. Okay, so the volume of that region can be found by integrating from 4 to 6, 2 pi, and then it's usually just times x, but that's when our area is attached to the axis of rotation. So if your area is literally adjoined to the axis of rotation, then it is just x. But since our x and this region is kind of separated from our axis of rotation, I'm going to take x minus 1 as our radius. Okay, so I'll have x minus 1. And then times the function itself, right, the height. So I'll have times 1/8 x squared dx. Okay, so actually evaluating this, I can bring the 2 pi out front, still going from 4 to 6. And then actually distributing, maybe I'll bring the 1/8 out front as well. So I'll just write the 1/8 out front. And then that just leaves the x squared to distribute. So I get x cubed minus x squared dx. So actually integrating, we're going to get 1/4 pi times 1/4 x to the 4th minus 1/3 x to the 3rd, and then from 4 to 6. Right? So continuing that, we have 1/4 pi, 1/4 of 6 to the 4th minus 1/3 6 cubed, and then that's all minus 1/4 of 4 to the 4th minus 1/3 of 4 cubed. All right, so I'm gonna go ahead and start typing all this into my calculator. I'm gonna see what this inner number is here. I'm gonna see what this number is. So give me a moment on that. Okay, so just that inner number is this 6/28 thirds. So I would have 1/4 pi times 6/28 over 3. So in other words, I have 6/28 over 12 pi. So 6/28 over 12 simplifies to 157 over 3. And this would be a number of cubic units. Okay, so just to look back, if we were to use the washer method, we would have to use a region or an integral through this space, and then a different integral through this space, because that inner radius changes, right? It's no longer just this constant function here, it's this part of the parabola. So if you were to use washers, you could do this with the washer method. You would just need two integrals. You would go from 0 to 2, and then from 2 to 4, or 2 to 4.5, and have need for those two separate integrations. With the shells method, we were able to just stick with one region, right? And this entire region just got folded over, and because of that, our integration is a little bit more simple. All right, that brings us to 6.4, where we're talking about arc length of a curve and the surface area of a generated solid. So this picture probably looks fairly familiar. This is meant to be like a Google Map or Apple Map type of situation, and we're going from here to here. Often you want to know how far this is, right? And more interestingly, we're often talking about the time, but if you wanted to know the length of this curve, there's some function going on in your phone that's calculating that for you, right? It's not just taking the straight line distance, because unfortunately we can't just go in straight lines from places where we don't want to be to places where we do want to be. We often have to like go around people and stuff, right? Kind of annoying where we have to go around things. So for that reason, and for other reasons, you know, if you have this rocket being launched and you want to know what is the length of this path of travel for this rocket, it's not just a straight line situation. This thing is curving through space. So you might need to program some ability for that thing to calculate the true length of its journey, not just like the straight line length from some source. For that reason, so what I did was I just kind of hypothetically came up with a function that would be similar to this path in Desmos. So in that would have been this function, something I found in Desmos. So it turns out that if you performed this formula, and I'm not going to explain this formula geometrically, but there is a geometric reason, that you get the true arc length. So you can see in the formula we have the square root of 1 plus the derivative of the function squared. So I would need to perform this calculation to find the true arc length of this curve here, which is supposed to model this journey here. Anyways, let's try one. Here's one. So it says, let f be 4/3 x to the 3/2. Calculate the arc length of the graph f of x over this interval, 0 to 1. Round the answer to 3 decimal places. Okay. Just to draw a quick picture, 0, if I plug in 0, I get a 0. If I plug in 1, I get a 4/3. So this would be 1.1, 1.2, 1.3. So I guess right about here. Just as an intermediate point, if I plug in a half, so 4/3 times 0.5 raised to the 3/2. So it's a little less than a half. So I'll just say right about here. So we're getting a piece of this curve. It's not a straight line. Okay, so we're going to be looking for the exact length of this portion of the curve. So the arc length, sometimes you just see AL as an abbreviation, will be found from going from 0 to 1, the square root of 1 plus the derivative of the function that we care about, and then we actually square that derivative, and then we'll go across dx. Okay, so we would have the arc length from 0 to 1, the square root of 1 plus, so we'll have 4/3 x to the 3/2. We need to take that derivative, so I'll say this little tick mark to represent that derivative still needs to be taken. And then also after that derivative is taken, I need to square. So what I'll do is I'll do the derivative squared part separately. So let's calculate f prime of x squared. So f prime of x, if I look at the function, right, take its derivative, so I'll multiply down by 3/2 and so on. So 3/2 times 4/3 x, and then we need to reduce 3/2 by 1, so that'll be 1/2. And then I need to square this, right? So squaring that, well, this cancels, I get a 2. 2 squared is 4. X to the 1/2 squared is just x. So 4x is the only thing that comes in right here. So we'll have from 0 to 1 the square root of 1 plus 4x dx. This will be the arc length. Right? So what I'll do is I'll go ahead and use a u substitution. So I'll let u equal 1 plus 4x. du would be 4 dx. So I don't have that 4, so what I'll do is I'll offset this by dividing by 4. So really, it'll be 1/4 du that comes in for dx. Okay, so we'll have the square root of u, and then times 1/4 du. What you can do is change your limits if you want. So 0, if I plug in a 0 for x, I get 4 times 0 is 0, and then plus 1, I get a 1. So my new lower limit would be a 1. Plug in a 1. 1 plus 4 times 1 is 5. So this would be my new integral that represents the arc length. So I can bring out that 1/4. I'll think of u, the square root of u as u to the 1/2, going from 1 to 5 du. Now actually finding the antiderivative, so we'll have 1/4, and then u to the 3/2 divided by 3/2, and then evaluating from 1 to 5. So simplifying that a bit. So dividing by 3/2, same as multiplying by 2/3. 2/3 times 1/4. Just woke up. Fraction brain is not on. So it's 1/6. All right, so we have 1/6 times u to the 3/2, and then from 1 to 5. Okay, let's plug this in. So 1/6, we have 5 to the 3/2 minus 1 to the 3/2. Right, so we get 1/6 times 5 to the 3/2 minus 1. This would be the exact arc length, so it's just a linear unit. It did ask us to round, so I'll just round this. So 1/6. and it said to 3 decimal places. So I'll go ahead and write 1.697. And that would be linear units, right? This is a length, an arc length. Okay. Moving on. Let's talk about one more thing. This surface area. So this is our last kind of important formula in this section. So the surface area of a generated solid, so imagine you have this curve, and then you rotate this curve around the x-axis, let's say. This kind of vase-like shape gets formed, but then this formula is not finding the volume, it's actually finding the area of the surface of this shape. Okay? So you can see it's similar to the arc length, right? Here's kind of the arc length piece, but then we're multiplying by 2 pi times the height of the function, right, to get the second dimension involved. So let's go ahead and apply this. I'm going to try this on example 9 right here. Okay. So it says, let this be our function over this interval, 0 to 1/2. It says, find the surface area of the surface generated by revolving the graph of f of x around the x-axis. It says, round the answer to 3 decimal places. Okay. So we'll have the surface area given as this integral from 0 to 1/2 of 2 pi times the function itself, 1 minus x, right? That's this piece, sorry. So here's 2 pi times f of x, here's my f of x, and then times the square root of 1 plus the derivative of this thing squared. So what I'll do actually on a separate sheet of paper is I'll figure out that derivative squared part. So I have this as my function. And what we want to do is figure out f prime of x squared. So just for the f prime of x part. So I'll think of this as like 1 minus x to the 1/2. So multiply down by the 1/2, I get 1 minus x to the negative 1/2, and then multiply by the derivative of the innermost, which is negative 1. So this would be the same as negative 1 over 2 times the square root of 1 minus x. Right? That's just the derivative. We then want to square this. Right, so I'm going to square all of this now. So when I square, we'll have now positive 1 over 4 times 1 minus x. In other words, 1 over 4 minus 4x, if I want to use that. Right, so that's the squared version. So I'll bring that back into the integral now. So I'm going to write 1 over 4 times, oops, this should be a 1 minus x. So that's 1 over 4 times 1 minus x, and then dx over here. Okay, so what I'm noticing is maybe it will be easier if I actually bring these two together. So maybe I'll work on simplifying this piece and see how that happens. So just to do another kind of scratch work to simplify this piece. So to get a common denominator, I would multiply by 4 times 1 over x. So 4 times 1 minus x, sorry. 4 times 1 minus x. So that's 1. And then if I add that to 1 over 4 times 1 minus x. Common denominator, basically. So this would be the same as the square root of 4 times 1 minus x plus 1 over 4 times 1 minus x. Just to simplify further, 4 plus 1, that'll be 5 minus 4x over 4 times 1 minus x. Okay, so maybe I'll write that now. So this would be the same as the integral from 0 to 1/2. Maybe I'll bring the 2 pi just out front at this point. And then I have the square root of 1 minus x times the square root of 5 minus 4x over 4 times 1 minus x dx. Bringing those together, the product rule for radicals says if they're the same type of root, I can bring their arguments together. So this would be the same as 2 pi, 0 to 1/2. This just one square root of 1 minus x times 5 minus 4x over 4 is 1 minus x dx. And once that is together, these can cancel. All right, so let's see what we have. We have 2 pi, 0 to 1/2. And then I still have the square root of 5 minus 4x over 4. And then this is times dx. And this square root goes all the way down, just to make that clear. So something I can do, I have a square root of 4 on the bottom, so I can bring out a 2. Right, so this would be equal to just pi. That 2 can cancel with the 2 out front. And I can just say now the square root of 5 minus 4x dx. So I've been able to whittle it down from this fairly complicated integrand to this not so complicated integrand. So at this point, we can let u equal 5 minus 4x. Then du would equal negative 4 dx. So in other words, negative 1/4 du would equal dx. I'll need a separate sheet of paper to pick this up on. All right, so writing all that out. So we still have pi out front. Then I have the square root of u times negative 1/4 du. All right, just plugging all this stuff in. I substituted out dx, and what replaced it is negative 1/4 du. I can go ahead and change my limits now. So if I want to switch my limits, I can. So plugging in a 0 to the substitution, my new lower limit would be a 5. Plugging in a 1/2 into the substitution, my new upper limit would be, well, 1/2 of 4 is 2. I'd have a 3 up there. We usually go from lower values to larger values. And if I do that, I would need to negate. So I'll just go ahead and negate. That way this negative 1/4 will turn into positive 1/4. So I'll have pi over 4, the integral from 3 to 5. of u to the 1/2 du. And this is representing, if you remember, the surface area of this original thing rotated around the x-axis from 0 to 1/2. So now, carrying that antiderivative out, so pi over 4, and then I have u to the 3/2 divided by 3/2, and then from 3 to 5. So dividing by 3/2, same as multiplying by 2/3. So we'd have pi over 6 times u to the 3/2 from 3 to 5. And then it said way back when to round to 3 decimal places. So pi over 6 times 5 to the 3/2 minus 3 to the 3/2. So that would be the exact amount of square units in that surface. But let's go ahead and approximate it. Okay, so to 3 decimal places, we're going to get a 3.133. That would be square units. All right, talk to you next time. Bye-bye.